Let's give you a proper introduction.
Okay.
Okay, so welcome everyone to Harvard Geography Colloquium, October edition. We are delighted to have with us today Dr. Keith Clark, Professor of Geography at the University of California, Santa Barbara. Dr. Clark received a master's and PhD from University of Michigan, specializing in analytical cartography. He's the author of 3 textbooks in 8 editions and over 250 book chapters, journal articles, and papers in the field of cartography, remote sensing, and GIS.
That's enough.
And he's told us that this, of all those publications, this is the most interesting, exciting one. So thank you so much for coming, and I'll let you take it from there.
Thank you very much, and it's nice to be here. And so thank you for the welcome, and thank you for the sandwich beforehand. That's particularly welcome. I'll admit it outright. This is a keynote presentation that I developed for the Chicago AAG meeting, where I gave the keynote presentation for the Spatial Analysis and Modeling Specialty Group. This is really, however, the report of 3 years of work, and it's actually 3.5 years of work that I've done for the United States Geological Survey Center for Excellence in Geographic Information Science. I'll give full credits at the end, but just to set the context, what we're doing is looking at the topographic content within the national map, which is this enormous, supposedly seamless map of the country, of which topography is a key element. So my title is On the Topology of Topography, and I've quite literally, within the last week, finished the paper, and it's almost ready to go out for peer review. So hopefully it will also be a paper. So the context is largely historical, and the history involves Harvard, funnily, so it's relevant history. And the context here is the mapping of terrain, which has come full cycle. If you think about the 142 years it took to map the United States the first time around, at 1 to 24,000, most of that mapping was done by contours, and those contours were interpolated by hand, largely by people in the field with plane tables and transits and theodolites, or occasionally sitting on a horseback with a note sketch pad and just literally sketching and interpreting the terrain. But we don't live in that era anymore. We rarely interpolate by eye. These days we use digital elevation models, digital terrain models, digital surface models, digital feature models. We use the triangulated irregular network, and more recently we use the point cloud. And when I think about the transitions that measurement technology has placed upon dealing with terrain, we've gone from just 50 years ago basically using, as I call them, unbelievably faithful reproduction of subjective contours in our digital maps to measurements at some of the highest levels of accuracy that you can imagine. Last week I was scanning the bluffs on the campus at Santa Barbara with a LiDAR, getting better than 2 centimeter, not precision, accuracy on those measurements. That's unthinkable levels of accuracy before. But of course this changes the accuracy, it changes the resolution. It's changed the emphasis, because when you image at a coarse resolution, what you primarily capture about the topography of natural features, the floodplains, the mountains, and so on. As you get to higher and higher spatial resolutions, you capture, in addition, features about human beings and their impact on the landscape, the impact of agriculture, forestry, urban areas, and so on. And then we have this historical legacy of algorithms. I'm going to go over it at some length from its very origins in just a minute, in which we devised methods for automatically extracting elevations from terrain and then modeling that terrain using something called the surface network. So I'll be talking largely about the surface network today, and it's the topology of that network that I refer to in my title, Topology of Topography. So I'm going to look at some of the recent trends, and I'll finish with some of the unresolved research issues, which I think are really important. So just to illustrate this, here's exactly the same area on the 10-meter NED, National Elevation Database, and I spent most of my career working at 30 meters. I thought 10 meters was fabulous. When you go down to 1 meter, you can see there are all sorts of features in the landscape that are just invisible when you work at the coarser resolutions. Now to set the context here, we have data, but then we also have mathematics, and mathematics of surface that I'll be dealing with here is surface topology. And of course, topology is the study of geometric properties and spatial relations unaffected by the continuous change of shape or size of figures. And the joke is that to a topologist, a coffee cup and a donut are exactly the same thing. So a topologist is somebody that can't tell the difference between their cup of coffee and a donut. So I'm going to give the long history here. And if we back right up to the Civil War, I just took a step into your memorial tower over here and saw the names of all the Harvard people that died during the Civil War. Here's some very famous topographic work from the Civil War, in this case in Virginia, where slope lines and Hatcher lines were pretty much the state of the art for mapping topography. And these are mapped pretty well here. So just lines that are suggestive of the downhill direction were just as formative before contours as contours. Contours, of course, date from Halley's work in the early 1800s and have been used a long time since. So if we go straight to the national map for the same piece of topography today, you can see that it's a contour layer that's the primary topography layer. But in addition, there are derivative DEM products from that particular contour layer. So history really goes back to the 1850s, and here, although we had contours, we were primarily mapping topography in the field with what might be called slope lines. Lines showing breaks in slope, or lines showing the downhill direction of a slope, what a skier would call the fall line. This is work based primarily on work by Arthur Crowley, who really is the sort of founder of this work. He was a Cambridge, England mathematician. He was an advocate of pure mathematics and introduced this idea of thinking about topography as representing a surface, and the surface being a mathematical surface that could be subjected to abstraction. So his key work just follows the Civil War, 1859, on contour lines and slope lines in the Philosophical Magazine and Journal of Science. And he begins this article by posing the idea, commenting on some earlier work, which he also cites, but he says, think of this problem as a problem of imaginary problem of topography. Imagine, to fix the idea, a mountainous island surrounded by sea in which we can simply vary the sea level. So I thought, perhaps to illustrate this, I should take a real island. This is Swans Island, Maine. It's just south of Mount Desert Island, where I was for a workshop at the beginning of the summer. But when we abstract it and put it onto, just take the contours and then begin to fill the topography, imagine that the whole thing is flooded and now the red parts are just breaking above the topography. You notice that as we flood the topography, some interesting things happen. Like points get isolated and then disappear and close, and then eventually, like these two peaks close together, and we get a saddle point pairing where we join two polygons. So if you think about the moving sea line as simply being changed in topology, it consists of loops around the contours. Occasionally those contours touch. Occasionally a hole gets left, and eventually that hole gets closed. Those are two very different points on the landscapes we might call peaks or summits and pits. And these are very formative around Cayley's original thinking, around how these points were related, how they were related to each other. Next comes James Clerk Maxwell, Scottish physicist known for his work on optics, in which, in this paper in 1870, on hills and dales, he credits the earlier work by Cayley, and says he's going to extend upon it and develop upon the idea that Cayley introduced. And he adds a figure, a graphic for the first time, to try and understand this. And he takes the original points, which Cayley had identified as being significant points within the landscape, the summits and the pits, and begins to talk about a network or a set of lines joining them. And he introduces his own terminology, which is, of course, completely different from Cayley's. I guess that's what academics tend to do. So he talks about summits and immits, or interior points that become pits, and then he has contour lines and so on. And he begins to suggest that we can connect these points together in a landscape. That if we start at a pit, we can follow a drainage line up to a summit in every instance, for example. And to suggest that there is a collective to these, that if we join the lines together, they create partitioning. And he calls these partitions hills and dales. And so there are upland areas and lowland areas. He deals with problems like this one, that we can have an elevated pit, essentially, at some elevation. That one's actually on the Swans Island, so it exists in reality. So out of this comes what gets called surface network theory. We end up with point features, and these are, at least initially, peaks, the summits, a local high point, a pit, which is a locally fully enclosed point on the landscape, and saddles, which can be simultaneously a high point and a low point in different directions. So you climb towards a saddle or a pass and go over it, you've reached a peak, but it's also at the bottom of the, usually the 90-degree feature. Then we have linear features that we, perhaps the most recognizable, the ones are called drainages or streams, which are going to be followed by the drainage system, although not always. And their opposite, ridges, which we recognize on the landscape, sometimes a break of surface, a break of angle points. Often they're somewhat more arbitrary. And we have areas, and these can be watersheds, slopes, or what geomorphologists often call hill slopes, or what Crowley and Maxwell called districts. So often included into this are other significant points, like break of slope lines, and we can find these today often with the software that's available to us in ArcGIS. Things like plane curvature, slope curvature, produce linear features when you map them out on the landscape. Maxwell's work was primarily about the numerical relations between the number of features of different types on the landscape, so he was looking for topological laws. The assumption was made of a homomorphic surface. In other words, it's continuously differentiable. It has a slope at every point, and it's continuously univariate. In other words, there are no double elevations for one point. There are no vertical cliffs, there are no caves, there are no precipitous sinkholes that disappear to the center of the Earth. So Maxwell's theory, the saddle points are the key, and if you could find the saddles on the landscape, you could trace upward to find a peak, and you could trace downward to find a pit. So that line that could be drawn, the slope line, would be a connecting line and therefore part of the topology. And if you're interested in this, there have been two absolutely thorough literature surveys of this literature by Raynor Morley in 2002 and Raynor in his dissertation in 2004 did an excellent job of synthesizing this material. Now we reached the point here in 1925 where the mathematics and the practical topography of this begin to diverge, because Master Morse in 1925 published this paper, Relations Between the Critical Points of a Real Function of N Independent Variables, in which he mathematically looked for the equivalence of these points on theoretical surfaces and produced equations that allowed you to solve for them. They don't always work perfectly when we deal with topography, but they certainly do for mathematical surfaces. And it was this work which inspired William Lawrence, right here at Harvard in 1967, in the Design Institute, to go back to and re-examine Maxwell's work from the 1870s and go back to this idea of the island emerging from the ocean with its contour lines and its pits and peaks and summits and saddles, to be able to partition those into the same regions that Maxwell defined as hills and dales, but also to recognize that these two regions in fact intersect. So you can have a part of the surface that is both a hill and a dale, which doesn't seem possible, but what it does is it produces a new set of lines, the course lines, that when intersected with Crowley's network produce what he called the surface network. So I call this a return to cartography because there's a reintroduction of Maxwell's ideas back into the practical world of mapping. Lawrence being involved in the early days of computer mapping, again here at Harvard. So Lawrence's contribution was quite considerable. In fact, many people call these Lawrence networks within the literature. So he did a pretty thorough review and summarized the prior work going back to Cayley. He returned to this idea of a topographic surface as something different from a mathematical surface, which had gotten Morse kind of sidetracked. He added to the set of regions. He intersected the surface network with the hills and dales to produce a new set of lines. He added this term of vergency. He talked about convergent and divergent regions. Convergent being those slopes or facets that were pointing towards a pit, and therefore were kind of trapped by the landscape. The holes in the original 3D diagram, and the divergent, or those that were draining to the exterior. He extended it not just to geography, but the primary purpose of his work was to apply it to economic geography. This was the era when geographers were interested in potential surfaces, so he was applying it to demographic surfaces and economic potential, and trying to use these ideas to regionalize these theoretical concepts so they could actually be applied on the landscape. But he also provided the first important links to computer cartography and GIS through the early work, which I don't have to tell you about since it took place right here. This work was later formalized by Faltz in a classic paper in 1974 as the surface network. So that becomes the classic paper. Now here's my digression. I know you did a historical symposium on the center last year, so was it last year or earlier this year? I can't remember. So I went looking for some of the early work to see if we could actually find it. And courtesy of Don Janelle, who's retired now at UCSB, I found copy number 1 with William Warrentz's own stamp on it of the Harvard Papers in Theoretical Geography, of which this early, in fact, the very first paper, Concepts and Applications, Spatial Order, dealt with this part 1 by William Warrentz, part 2 by Mike Waldenberg, that dealt with essentially what I've just been talking about. It's kind of hard to believe that all that happened before the computer was capable of actually doing computations on these surfaces and storing real data that had to do with topography. So when the computer comes along and enters the equation, things get complicated. First, the first generation of computer mapping software, and this is SciMap, right from here at Harvard, were quite awful. I mean, they were just terrible at representing topography. There were so many sources of error. So these white separation lines were meant to be the contours. Even when we take that and begin to do things like simulated hill shading, it's still got so much error in it, so much inaccuracy that we can't really see some of the features that we're talking about. Then comes another Morse, not the original Morse. This is Stephen Morse, 1969, who was trying to solve a very particular problem. And it had to do with aircraft navigation. It was quite possible at the time to use technologies to measure the actual altitude of the aircraft and to use the height of the aircraft then to find the height of the ground. And the problem was, how do you then use contour maps to figure out where you are on the ground with respect to how high the aircraft is at any point on the Earth's surface? So he went back and reviewed some of this early work. He realized that contour maps could simply be encoded using Freeman codes, which are simply vector codes for vector features that are stylized and have only 8 principal directions. And he coded saddles as branch points within the topography and took advantage of this knowledge that if you went up from a saddle, you would come to a peak. And if you went down from a saddle, you would come to a pit. And used this to produce a decision tree network that allowed you to, given that you knew your elevation, you could sort of solve a logic problem and arrive at a single polygon on the map, which was your possible location. So this was critical to Strategic Air Command and so on. They had another way of navigating. Obviously, they were going to go a lot further with this kind of positioning. But it interestingly reduced topography to a decision tree, or to a set of logical decisions about which elevation you were actually at in the landscape. So Faltz's work was clearly influential here. Faltz on surface networks said there are practical uses. One means a condensed surface description. And much of the early literature saw digital elevation models, even at 90 or 100 meters, as being massive amounts of data. So the desire was to actually compress them, make them smaller. They would have had nightmares if they knew about 1 centimeter digital elevation models. Condensed surface description, particularly since they may be used as a directory in conjunction with computer representation, and therefore support automatic abstraction processes, and this idea of abstraction being the surface network. So this is a new idea. This is a surface network as a data structure, but also a symbolic or an abstract representation of a surface. And both of these are useful purposes. The second one, the abstract representation, went on to become the computer graphics industry. The first one as a data structure went on to become much of GIS. But how do we extract these features? This is an issue. So here we begin to get much more solid links between this theory and the world of GIS. So Plecker and Douglas produced this critical work on critical point detection. How do you take a digitalization model and extract from it that subset of points which are candidate peaks, pits, saddle points, and so on? Which are the ones that are likely to sit on the critical surface network? Fowler and Little did a very interesting paper back in '79. We've just been recoding this method, and it's pretty prescient. They looked at a point labeling method that simply says, we'll scan the whole topography and see what each point could possibly be, and then just keep eliminating what it could not possibly be, and come up with a set of candidate identification labels for each point. And these are quite good at finding the critical points. Haralick in '83, again out of the computer graphics literature, introduced this idea of zero crossings, how many times a line goes from, say, generally trending left to suddenly trending right. Each time you do that, we call that a zero crossing. It's across the primary vector is cross directions. And counting these allows the sort of the encryption of topology and a great many other things. And then all of a sudden we saw the idea of the surface network being discovered in hydrology. And stream network extraction became the key issue. How do we extract from a digital elevation model the likely location of stream segments, rivers, potential flood points, and so on? And David Mark and O'Callaghan, an early paper, and Jensen and Domingue, a classic. My own former colleague, Larry Band, wrote 2 classic key papers while he was an assistant professor on this. Moore, we haven't talked about the Moore network these days. They used methods for automated extraction of the drainage network from the digital elevation model. It's only part of the surface network, but it's an important part. Wilson and Gallant started some key work back in '96. They put into the public domain a huge Fortran package called Tapes G, which, believe it or not, when you dig down far enough in most of the open source software, you still find lines of code from Tapes G in the feature extraction algorithms in most GISs. And Joe Wood at London, what's it called? London University? City University of London, wrote for his doctoral dissertation an open source, a public domain package called Landsurf, which does a fabulous job of dealing with topography and extracting the surface network. And this open source code began immediately to be scooped into the broader software packages, sometimes with acknowledgement, sometimes without. And most of these algorithms began a series of standardization discussions around this idea of network surface flow. So here's Bob Haralick's work in image processing. His problem was applying this not just to ridges and valleys, but also to digital images, captured digital images from air photos and so on. But being able to extract continuous surface lines that represent elements of the surface network was his key problem. And he immediately found this, which is an essential problem, that these lines are discontinuous, especially at coarse resolutions. It's impossible to trace a single ridge line or a single drainage line without losing it at some point. So an enormous amount of the literature deals with that issue. This idea of zero crossings, if we start at the kernel point in a single pixel and go around it, we simply ask, if we take each one of those 9 elevations surrounding it on each direction, how many times do we go from one direction to another? So zero crossings became the important part of many of the algorithms, counting the number of zero crossings and dealing with it. Then we saw these flow accumulation methods that start with the raw digital elevation model, realize that pits are a problem, so they simply take the pits and fill them up until they reach their overflow point, and then they simply calculate flow direction for every point on the surface, and make the assumption that water is always going to go down the steepest slope available to it at any point. And that allows you to calculate for any point on the ground the number of pixels that are upslope from that point, and that therefore would drain into that point. We call this the downslope flow accumulation, and almost all the methods that currently do drainage feature extraction from digital elevation models use this idea, and they simply threshold. They say when the cumulative number of upslope pixels reaches a certain number, then this is definitely going to be a stream. The problem is often these lines come out more than 1 pixel wide, so we need to thin them. We often need to prune them. We need to decide when you stop a stream, because if you followed streams with most algorithms, it will go all the way up to the summit. You don't necessarily want your streams to emerge from a summit. You may want to prune them at some appropriate point, and you may need to connect discontinuous points that come from various networks. So this problem of filling pits, so here's an interior point that is a pit, so we have no downslope flow from that point. So if we lift it up to its nearest overflow point, which would be here, we solve the problem. The problem, though, is that when we get into, say, detailed measurements of very flat areas, almost everything's a pit. So you end up with creating some very spurious drainage feature lines when you get into very low variations in topography. So some of the issues here, specifying the neighborhood, the huge war between the D8s and the D4s. Do you choose the 4 nearest neighbors pixels, or the 8 nearest neighbors? Do you choose a broader neighborhood? Do you allow diagonals or not allow diagonals? So choosing the neighborhood turns out to have a pretty important impact on where the river goes. Some of the more sophisticated algorithms actually allow you to split the surface flow between different target pixels, so that part of it goes in one direction, part in another. Dealing with edges, especially things like coastlines, becomes an issue. Pit filling I've already mentioned. Flat zones are particularly weird. You end up with having to, for example, if you've got topography that includes a lake and you know it's a lake and you've got the elevation of the lake, you still have to route your drainage across the lake in some way. So it's sort of counterintuitive. We often have discontinuities in the surface. We have ends of features which simply disappear, as I said, like the upstream segments of the surface network. And then, of course, all of these are impacted by scale, the scale at which we're mapping. If we're mapping at the level of the entire Mississippi basin, we're not particularly concerned with level 1 streams. Resolution, as we get better and better resolution, we see more and more of each of the features of the surface network. And then granularity, what is our minimum size measurement within the system? These all have a significant impact. So just to illustrate this, here's a piece of Santa Cruz Island in California from the 30-meter NED, and of course it looks blocky. 30 meters is blocky. So when we apply any one of these algorithms, we end up with discontinuities. So here's, where are we? Purple is peaks. So here's a peak, but we've got a break between the peak and the appearance of the first stream, but also a break in the appearance of the ridge, which may or not be intuitive. You might want your ridges to connect to your peaks. When you take this to the extreme, so here is, that says 30 meters, that's actually 1 meter data for Santa Cruz Island from LiDAR. When we get down to the level of the entire sub-basin, and now we begin to see details like individual arroyos here, or roads, tracks, jeep trails, and so on, individual boulders sitting on the landscape, and then in particular for Santa Cruz Island, these little mudslides that go down slope. Every one of those sort of generates its own topology and can or cannot become part of the surface network depending upon our decisions. When we run the algorithms, which doesn't show very clearly, but you see we need to make choices about how we prune the drainage network, because we can't follow every single one of these little substreams off at the head of the stream. Santa Cruz are mostly dry most of the year anyway, and especially right now. Here's a little better detailed example. You'll notice that here's a ridgeline coming down. Now clearly that extends down here, but the concept of a ridge becomes less and less clear and less crisp and less detectable by the algorithms as the slope begins to ameliorate. And you notice that as we go down a stream, we get a lot of pit solutions occurring along an individual drainage. Doesn't make sense, but when you think about it, it sort of does. So the level of detail obviously is extremely important. So if we go back to Swan Island and go back to 30 meters as our basis and run a solution for the whole island, we end up with a mess. Here are the same color labels for all the features. You see that yes, we have drainage features, yes, we have ridge lines, yes, we have pits and saddles, but essentially we're just not looking at it at the right resolution. So I hope I've got time to speak for a few more minutes here. Let's talk about some of the more recent literature. So since the turn of the century, we've seen a lot more algorithms and a lot of very good literature reviews, as I implied, Renner's in particular. We've had very much better visualizations, including especially the work of Helena Mitasova, who's done some extraordinary work around topography. We've seen exploration of this idea of scale sensitivity, including by myself. We have far better hydrologic models now in which the surface network actually becomes part of the hydrologic model. We've seen links back to Morse theory, primarily coming out of the computer graphics industry, especially the video to support modeling for cartoons and so on, where they have to abstract three-dimensional surfaces. Morse theory has proven very valuable there. We've seen three-dimensional extensions to the two-dimensional surface network theory. I'd say the biggest impact has been the rise on the use of, or the concepts of uncertainty, an incorporation of uncertainty into the surface network theory. And this has been both metric, from the point of view of taking measurements of the landscape, and also semantic, in how we define the very features that it is that we're trying to identify. So let me just cite one of these, partly as a tribute to Pete Fisher, who died last year. This paper in 2004, well, where is Helvetian fuzziness of multiscale land morphometry? It was kind of a key paper in this early work. And here he used the toponymy of the features themselves. So what's a mountain? What's a ridge? He computed for 6 different feature types. He computed the fuzzy membership values of each pixel into those different feature types. And then he aligned the fuzzy surface terrain network with labels to gauge the location and extent of the regions. So now we can use them to fuzzily define Maxwell's regions on the surface, and therefore to actually compute the extent of things like mountains or valleys. And notice that this was sensitive to the labeled features, the types of the features, but also to the scale. He used these 6 model classes. He used channels, peaks, plains, as he called them, passes, pits, and ridges, and was able to produce these fuzzy membership surfaces for each of these features. So this is not a surface network diagram. It's the likelihood of any point on the surface belonging to one of those classes. And if you choose the one with the most likely class, it's obviously a good chance that that one's going to be correct. So he used this primarily to say, can we actually put a spatial extent on a particular mountain, on a particular valley? In our own work, we've been looking at feature type uncertainty due to both scale but also methods. So we produced a series of scripts that allow you to bring in topography to run all of the algorithms at each one of a series of nested spatial scales, to run alternative algorithms for classifying the features, and then to accumulate the probability of each feature type in the same sense that Pete Fisher was working on this. And then we can talk about the membership of the highest class, and you notice that we've got the effect of multiple scales being visible, in this case in the drainage network, and we've got things that are much more certain peaks and much more certain pits because they identify in the darker colors. Now, what was a complete surprise to us in this work is that we thought that features were pretty much mutually exclusive. In other words, if something was a pit, or if it was a summit, let's say, it's always going to be a summit. But no, summit can, at some appropriate scale, can become a pit, depending upon your sampling and how things work. So in fact, any point in the landscape has a potential to belong to any one of the feature types, which is kind of intriguing when you think about it. So a little bit of discussion around some of the issues. So the good news around surface network research is the research and publishing remains quite vigorous. There's a lot of interesting things going on. In the meanwhile, we now have more surface elevation data than you can shake a stick at. On my terrestrial LiDAR, I can press the button, and 5 minutes later, I have half a terabyte of terrain data as a surface cloud or as a point cloud. It's extremely accurate. I can often tie it directly into GPS. It has very high levels of resolution. It's rarely now in grids. It's usually in a point cloud format. So I've got a new data model in which to apply these network solutions. We have an enormously broad choice of methods to compute and extract the surface network, but we've reached a point where if I gave an assignment, let's say in a GIS class, I said, go and download the topography for this piece of the Earth's surface and extract the surface network and make a map of it. If I assigned that to 30 students, took the 30 maps and overlaid them, I'd have something that looks a lot more like my uncertainty diagram than an actual solution to the surface network. So it becomes somewhat subjective. The methods are available now in many GIS packages. They're contained in ArcGIS, in particular the ArcHydro module, within GRASS, which has some very good implementations, MapWindow, Saga, QGIS, Landsurf. I know you've used many of those. It's promoted the use of a surface network as a tool for data modeling, analysis, and applications that now extends far beyond the realm of computer maps and digital terrain models. So the National Hydrographic Database, for example, uses this idea of nested watersheds. Each surface facet classified as a watershed and then sub-classified depending upon the branching network is how the NHD data set was constructed and coded. Many times planning models or analyses simply assume that there's a finite watershed. A lot of times ecological models assume that a watershed is a finite polygon around which there is no uncertainty, and that becomes the boundary for your planning map. But certainly it depends on, as we've seen, it depends on a large number of different features. And then there are important new and I believe fairly exciting links between the feature types, between the ontologies, what exactly is a mountain, what exactly is a ridgeline, but also toponyms, the fact that we've got a global databases of features that actually show names on them, the ridges that are named, summits that are named as summits, that we can use to test hypotheses about these models. And increasingly also incorporating the use of uncertainty, I think, is a promising way forward. And of course, there's bad news as well. The single solution approach that computes a complete and unambiguous network automatically for any terrain model. If somebody tells you they can do it, they're lying. Because it's always going to come out different, depending upon which choice you make of algorithm, what scale of data you have, what source of the data was, and so on. The networks are discontinuous, and in some places simply because algorithms don't work, some places because the very definition of what it is you're looking for is vague, sufficiently vague that the algorithm's never going to give you a solution. In other places, it's absolutely clear. So and the irony is you would think that it would be most clear in very rugged terrain, very clearly defined topographic features, and least clear in areas that are pretty flat. Well, often it's just as ambiguous in rugged terrain as it is in flat terrain. There are major scale sensitivities. We know, of course, in geography that scale matters. Choosing the appropriate scale remains a problem. Using the software itself is still both an art and a science, and teaching it is even harder as a consequence, because part of it's teaching the art. Flat areas in general work worst, but if you say, what are the applications of this technology? The most critical ones are in flood modeling and in modeling sea level rise. And both of these are essentially near zero or near total flat, and yet it's where our solutions need to be the best. And often they are the worst or the most ambiguous. And then, of course, we make these assumptions of no discontinuities, whole or interior spaces, and the ability to map with LiDAR things like caves, building interiors, underground structures means that a true three-dimensional model of these remains elusive. In particular, even the incorporation of things like underground tunnels and drainage culverts under roads is hard enough in the landscape, let alone when you're truly trying to model hydrology. So in terms of where next, It's now possible to bulk mine entire countries' terrain at high resolution. You know, I used to think of the digital elevation model as 1 7.5-minute quad, and now I think of entire coverages, like the whole country, equivalent of 7.5 minutes. Bulk mining topography in entire countries allows us to do things like actually regionalize the variance in topography and apply different algorithms in different landscapes, which is where we started from with the CGIS work. So what are the spatially convergent patterns? Where can we say that a particular algorithm, let's say D8 and downslope flow accumulation, will always work best? And can we automatically select that algorithm to use in that type of terrain? What types of features get labels and therefore could perhaps be solved as parts of the terrain? So if we think of a valley, let's say Silicon Valley, whatever, any good example of a valley, can we say, well, that has nice crisp edges and you can clearly define precisely where they are, and therefore can I get labels from things like topographic databases that have labels in them and use them to identify these features? Could I develop an algorithm that would, say, data mine the topography on Mars and be able to label all the mountains as mountains and label all the depressions as depressions and so on? And then we've got a very long history now of naming features on the Earth's surface. So we sort of have an ontology of surfaces that we've applied, but we don't label every mountain. We don't label every summit. We don't label every ridge. Why do we choose to label a particular feature and not another? These are interesting problems in which we're moving right now. And then does terrain surface theory generalize to all surfaces in 3D, let alone higher dimensions, is something we're concerned with right now. So what got me interested in this work originally was this idea that if we can have a simple solution, let's say we have a nice, relatively straightforward set of contour lines, no slope lines on here, that we can solve, let's say, for a simple surface topology, and it is just simple network. And then we go about classifying, let's say, slopes that face in a particular direction that represent drainage course to ridge, and they become repetitive. So let's say we go, let's just call them green and white, green, white, green, white, green, white, green, white. If they radiate around a particular feature, can we use that radial property to define this as a summit of a particular type? That holds some intrigue for me. So where we are right now, we've been looking at topographic names. We've downloaded the entire geographic names information system into our own browser so that you can specialize. So here is everything labeled as a summit in the geographic names information system, or at least for the Western United States. So here's a single example, Summit Mountain. And you notice that there are more summits in the west than the east. So we do have some geography of GNIS, but there are also depressions, hollows, all these names that are culturally sensitive that also represent topographic features that we have to investigate. Okay, so that's, I hope I've, pretty much on time. I've left myself some time for questions. Good. I should point out my sponsors here, the USGS Center for Excellence in Geospatial Information Science, in particular in Worcester, who is deeply involved with our Spatio-Temporal Center, and indeed is serving as our sort of chief of our board of advisors. My co-author on this particular work is Bo Romero, who's one of my PhD students, and a co-author on the paper on the topology of topography, which is shortly to go out for peer review. So I believe that is it. Yes, thank you.
Thank you very much.
Questions? Yeah. Yes, sir.
I'm curious about kind of cross-pollination between industries, which is kind of this revolution of laser scanning and the creation of surfaces. How much do you see the theory you're talking about here being applied to other industries